Okay, I'm sharing the screen, so please confirm that you are seeing the title of the presentation and we will proceed. Okay, thank you. And let's start. Okay, so our topic today is called Principles of Blockchain Functioning. And what are we going to talk about today is more deeply about how blockchain works and what are the core principles that actually make blockchain called blockchain. So first of all, let's look at what are the different contexts in which we can talk about the word blockchain. So the first context is when we are talking about specific blockchain. For example, we can say this is a Bitcoin blockchain, or this is an Ethereum blockchain, which means that we are referring to a specific chain of nodes which is being supported and which is being added according to the rules of the specific protocol and specific system, because each accounting system, each protocol, and almost each project has its own rules, its own structure of the block, and its own or at least a little bit different cryptography. We are not talking about the forks right now. We are talking only about unique projects like either public blockchains like Bitcoin, Ethereum, Monero, Zcash, and others, or about permission blockchains like Hyperledger and whatever Hyperledger is doing right now, for example. The second context in which we can refer to the word blockchain is as the technology. And during the last lecture, during the last couple of lectures, we had this overview as the technology, and we are going to continue with this route today. And the third context is implementation of technology in a particular case. So this is when we are speaking about, not about Bitcoin or Ethereum or whatever other accounting system, but how blockchain works and how blockchain behaves when implemented in a particular case. So not on the high level as the blockchain, as the technology, as an approach to organizing and synchronizing data, but as specific protocol, for example. The general definition, continuing the one we had before, but phrasing it a little bit differently and looking at it at a different angle, but still maintaining the same idea. Blockchain is a technology for storing, reconciling, and synchronizing data between participants who do not trust each other. And let's spend a little bit of time unpacking this definition. So technology is understandable. For storing, this is also pretty straightforward because whatever we put in the blockchain, we put it to store there, ideally for an indefinite amount of time. So this is not really a data processing technology or data manipulation technology. This is, first of all, data storage technology. Reconciliation means that there are several parties who need to agree on the single state of this data storage. And this process of reconciliation can be done in many different ways. In Bitcoin, for example, this is done through, first of all, proof of work mechanism and through the rules of the protocol, which ensure that every node that follows the rules and has unmodified Bitcoin software stores the same copy of the data storage. And whenever someone tries to modify their own copy of the storage, all other well-behaved players will be able to quickly see that without spending too much of their computational power, and to exclude this unlawful player from their lists. This is the process of reconciliation. And synchronization means that, again, we have many participants. Many of them are distributed not only geographically, but they are also in different subnetworks. They can have different hardware underlying of these participants of the system, and many other different aspects, even different software protocol versions, because if you look at Bitcoin, for example, not all of the nodes are running the latest software version. Some of them are running a bit older versions. Some are even running very, very old client versions, which practically exclude them from participating in the network. And this whole concept of synchronization allows all of the participants in the system to make sure that they always have the same state of the database, as long as they are playing by the rules, of course. And participants who do not trust each other, this is where we rely mostly on cryptography, because either you play by the rules and you do what the protocol says, and you basically obey the math. You do not obey the rules that someone made up or some superstitious set of rituals, but you obey the cryptography and the math, which is under the hood of the protocol. On the other hand, if you do not want to behave well and you want to cheat, this will be quickly become clear, and no one will accept the version of the history or the data or whatever else you are trying to propose to them. And this is one of the most important features of blockchain as a technology, is that it allows to operate in the environments with absolutely no trust among the participants. When in many conventional systems, in many client-server relationships, you always have some party which you need to trust. If you, for example, open your banking app one day and you see that all of your money is gone, let's say all of your money is gone, you practically have not many proofs to say that you had the money in the first place. You can have some screenshots, you can try to get the transaction history through your bank directly or through your bank administrator, whatever. But for everything you see in your banking app and everything which you have on your banking card, for all of that, you have to trust the bank itself as an institution, as the service provider, as an unknown party in which you trust for some reason. So, or for any kind of conventional system, not only financial, but also like social networks, like email or whatever. Whenever you use this system, you need to trust the one who provides you the services. So let's say if your Gmail, or not your Gmail directly, but the whole Gmail gets hacked and hackers obtain the access to the database and they remove one particular email from your inbox, you will have no way to even know that it was there in the first place, because you blindly trust the service provider to always provide you the relevant, true to life and consistent data, whether it is banking balance or list of emails or whatever else. This is a trustful environment. Blockchain can operate in trustless environment, where we, by the default, we presume that everyone can be an enemy And that's why we trust only the math and only the rules of the protocol. So at the technical level, blockchain can use any database because, again, blockchain, it is a technology and a way to organize data. It doesn't dictate that you have to use Oracle database, or you have to use relational database, or you have to do something else. It is a way to organize data. Where do you store the actual data? It is up to you as a developer, as a creator of the protocol, because as we see, for example, when comparing Bitcoin and Ethereum, Bitcoin has a model where all of the balances are calculated based on the inputs and outputs of transactions, while Ethereum nodes have a special database where they keep the account balances of the accounts they know as the cache layer. So Ethereum, as you may or may not know, has account-based model. And in addition to the records in the blockchain, they have this account database, which acts as the quick access layer to quickly obtain the state of the account. But again, it's still trustless environment, and you do not need to trust your node because the data is reconciled and synchronized between the parties. Next point here is blocks are formed from transactions. Of course, some blocks may have 0 transactions, but the structure itself and the hierarchy is that we have that transaction which contains something which we will describe later. And when we batch few transactions together, we get the block. So block can have 0 transactions, block can have 1 transaction, or up to certain amount of transactions, which is dictated by the protocol. But the hierarchy remains the same. And well, this process is more or less similar to for all of the blockchain-based systems. A transaction in the context which we discuss here is a digital application for the transfer of ownership certified by an electronic signature. And what it means is that basically any kind of transaction is a transfer of ownership. When I give you $5, I am transferring my ownership of this $5 to you. Or when I'm gifting you my house, again, I'm trusting the ownership of my house and I'm giving you this ownership. You are the new owner of this house, this $5 bill, or whatever else. Here, we are operating on the digital level. So the transaction in the blockchain is a record which specifies who transferred ownership to who and what is the object of ownerships. So who are the subjects and what is the object of this ownership transfer. And of course, in order to somehow prove and to certify this exchange of ownership, we use electronic signature. Just like when you sign the paper document for gifting the house or selling something or making a big transaction, big money transaction, you do the same for digital transactions. But instead of your hand and a pen, you use electronic signature, which is generated using your private key. Accounts in blockchain-based systems are associated with a public key. The public key is the primary identifier, which is used for, first of all, differentiating between users. This is pretty obvious. And the second, it is used for well, not exactly in this context, but in asynchronous crypto systems, this is used to encrypt something, to encrypt some piece of data and to pass it to the recipient. But in our case, this is used as the primary identifier and for verifying the signature, because whenever I want to verify someone's signature, I cannot ask them for the private key every time, and I shouldn't even ask them in the first place, because the private key is called private for a reason. Whoever has the private key has the access to all of the assets and all of the balances that this private key manages. But in order to, for me as the third party watcher, in order for me to verify that this transaction is valid, I take the public key of the person who generated this signature. And the last but not least is a cryptographically stable hash function is required to link blocks. This means that basically blockchain on a very, very simple, very high level is a linked list. There exists such a data structure as linked list. And in addition to the actual body of the block, we need to have a part of the block which points to another block. And this pointer in blockchain-based systems is the hash of the previous block. And in order to generate this hash, a stable and strong cryptographic hash function should be used, because otherwise any malicious party could forge this signature and could hash this hash value. So instead of sending money to you, the money will be sent to the arbitrary player. Here we have a more visual representation of the blockchain structure, and let's look at it a little bit closer. So any blockchain-based system, any system which has a blockchain as its main data organization technology, has more or less the same look. So we have a sequence of blocks. Each block uses the hash of the previous block as the pointer. So if I look at the top block in this list and I want to traverse this data structure and I don't know, verify transactions myself, in order to do this traversing, to go from one block to another, I look at the hash of a previous block and request it, go to the node and say, give me the block with this hash. Then when I obtain the block, I see the list of transactions and the hash of a previous block. So for example, if I want to verify these two blocks, again, it's a very, very simple example, and it's not fully describes real life, real world blockchain-based systems. But on a high level, I take these transactions, I combine them together, for example, by simply concatenating what is inside of these transactions, and I hash them with a hash algorithm which this protocol supports. And if I get the same hash which is specified here, I can be sure that for these two blocks, they are valid, and the sequence between these blocks is valid. Then I traverse further and further, and eventually I get to block 0, which is also often called genesis block. And its biggest difference is that it has no previous transaction hash, because it is the first block in the chain. Usually when the new system is deployed, its creators pre-generate the genesis block and put some arbitrary data or put no data at all inside of this block, and then the process goes as it goes usually. Next block points to the genesis block, and so on and so on. When creating any application or any service, product, software, new system, we ask ourselves an array of questions. What technology to use, how to organize the data storage, how to protect our system, and now more and more entrepreneurs, system creators, developers, companies are asking themselves, should we apply blockchain? Should we invest into making our system blockchain based? In order to answer this question, of course, this list is not exhaustive. It's only a few points that we want to look at here, and the ones that are most important for us inside of this course. But anyway, these questions are still important. So first of all, it makes sense to apply blockchain when it is necessary to carry out storage and accounting. So whenever we need to store some data in a sequenced manner and to do the accounting, like whether it is accounting of financial transactions or accounting of warehouse, for example, or whatever, this is one point for blockchain. Next case is when we need to transfer assets between users. And asset is pretty vague term in the modern market, because there are many definitions. Some of them are closer to truth, some of them are farther from truth, but generally asset, it is something that we want to own. This can be a digital asset, this can be a representation of some ownership, this can be a commodity, for example, and there exists a need to transfer this ownership rights. So for example, if we are doing a marketplace, like let's imagine blockchain-based Amazon, for example, then the product itself can be an asset. Or a better example would probably be an eBay, where I, as the seller, own some valuable asset, and I transfer the ownership of this asset to the highest bidder. So whoever pays the most, I transfer them the asset. And this is second point for using the blockchain. And the third point is when several independent parties are involved in the management of the accounting systems, and these parties do not trust each other. So again, we have already discussed it pretty exhaustively, so I will not stop too much here. But generally, if you have 3 of these points, usually it is a very good idea to at least give it a thorough thought and consider using blockchain inside of your system. Blockchain, like any modern, relatively young technology, has grown with many myths that people get wrong. So the first here is that blockchain can verify any data. This is mostly the question of how you phrase the question. So blockchain is not really verifying anything. The verification of the data itself is on the business layer. So blockchain does not care if you are writing incorrect data inside of it. The only thing blockchain cares about is that structure and cryptography are in place. If I start, I don't know, writing some stupid predictions in the blockchain, there's no even way to verify them. So I predict, I don't know, I'm some kind of astrologist and I just put random things inside of the blockchain, who will verify them? Well, whoever, but not blockchain. Blockchain is for storage, reconciliation, and synchronization. Blockchain supports instant transactions. And again, this is the problem of phrasing the question not really correctly. We are looking not on the blockchain here, we are looking at the system. Blockchain itself, it's just for storing something. It's not about the time, not about instancing, not about I don't know, transaction processing time. This is the different level. This is the protocol level, which highly depends on the kind of data we have, the kind of verifications we need, and so on and so on. Why Bitcoin has around 10 minutes of block processing time? Because this is the protocol level limitation. This is the, I would say, even consensus level limitation. This is not the problem of the blockchain. This is the problem of the system in which blockchain is applied. Data in the blockchain cannot be changed. This is a more tricky one because we are used to believing that blockchain is immutable, and of course it is, but the complete trust in, again, blockchain as the data storage technology is wrong, because the process of ensuring the immutability of the blockchain is, again, a protocol level limitation. Let's say I create my own blockchain and I am the sole owner, the sole node, the sole validator, whatever. Who will prevent me from going all the way to the beginning, changing something in the first block, and then simply recalculating all of the hashes? If I'm the one, if I am the single player, if I control everything, I do not need to prove anything to anyone. I can just spend this time, recalculate the hashes, and move on. So basically what I have done is I have changed the data inside of the blockchain. The blockchain is encrypted. When we say that blockchain-based systems rely on cryptography, it does not imply that blockchain is encrypted. Again, the task of protecting the integrity and the privacy, importantly, the privacy of the data inside of the blockchain is, again, guess what? The problem of the protocol. Because blockchain, just like a regular database, you cannot say that my relational database is encrypted just because it is a relational database. It is encrypted because I have applied an encryption algorithm either before putting the data into this relational database or after I have stored it there and I have encrypted the data after I have put it in the database, or I have encrypted the access to the database, or whatever. The same goes for blockchain. Either you encrypt the data before, or you do nothing, because you cannot encrypt the data after it was put into the blockchain. But blockchain itself is not encrypted, and it does not encrypt anything. The last but not least sounds like this: blockchain can replace industrial servers. And this one is the most this is the kind of question that someone who has very limited knowledge about blockchain and decentralized technology can ask, is that, well, why don't we all move to the blockchain? Like, screw the crowd, the cloud servers, all of these infrastructures, Azure, AWS, Google Cloud, whatever. We don't need them. We just use blockchain. This probably will never happen for the reason we already discussed, is because blockchain has sense to be implemented only in certain use cases. It makes absolutely no sense to migrate all of the services into the blockchain. It will just you will just shoot yourself in the leg with a shotgun, and no one will be happy from that. Only use blockchain when it makes sense, and that's why it will never happen. And industrial servers and cloud providers will probably exist at least for quite some time. What are different criteria differentiating blockchain protocols, blockchain-based protocols? First is public or private. Public means that the chain itself is open and can be audited by anyone. Private means that the chain is not available to anyone, but available only to the parties who are maintaining and participating in the development, not development, but in the progress of this chain. Then we have permissioned and permissionless. Permissioned basically refers to a category of blockchain-based protocols like Hyperledger and other corporate level blockchain-based protocols. And what it means here is that in order to become a validator, you need to get an invitation. Permissionless systems, on the other hand, mean that you have some piece of hardware, you download the software, and you're good to go. You're on the same level as everyone else, and you also become a validator. You do not need any special kind of invitation. The third difference criteria is consensus mechanism, and here we get into this rabbit hole of proof of work, proof of stake, Byzantine fault tolerant, PBFT, FBA, and many other consensus mechanisms that protocol creators use in order to secure and to provide a way for reconciliation and synchronization in their systems. So a brief refresher: public is anyone can access transactions and conduct audits. Private, only predetermined parties have such rights. Permissioned, anyone can become a validator. Permissioned, only specifically designated parties can be validators. And usually you need to have some kind of invitation. Speaking about consensus mechanisms, of course, we have proof of work, which is used in Bitcoin and in many other blockchain-based systems. Its main features are the number of validators is unknown. When looking from the standpoint of a single validator, you do not have the map of the full network. You only know your nearest neighbors, and you are interacting only with your nearest neighbors. That's why it has to be ready to operate in an environment when there can be 1 million validators or there can be 10 validators. It needs to maintain its effectiveness and its features as the, protect the features of the blockchain. Validators are anonymous and have no reputation. So basically, if you see that someone is behaving incorrectly, there's no report button. You just remove them from your list. This is up to you. The voice is supported by proof of work. So you are voting by participating or not participating in this proof of work race, this race to add a new block. Consensus is reached if the parties that control most of the power agree. So here we have the rule of 51%. Whoever has 51% of the power is basically controls the state of the blockchain. And if this 51% is distributed between different parties and they all have the same state of the blockchain, we consider that these parties are in the state of agreement. In addition to Bitcoin, examples of systems that use proof of work consensus is Monero and Litecoin, which is a fork of Bitcoin. Proof of stake, in proof of stake, the creator of the block is determined by the algorithm. So unlike in proof of work, where we have this equal rights, equal race to add the next block, proof of stake has the algorithm which ideally should ensure that validators and block creators are rotated in some democratic manner, let's say it like that. The chance to vote is proportional to the balance. So in simple terms, the more coins you have in your wallet, the more likely you are to be the next creator of the block. The validator loses his coins if he certifies incorrect or conflicting blocks. Here, what we see is that we have a financial incentive to play nice. If you don't play nice, you get bonked on the head and you lose your money that you have been staking and using to participate in the consensus. Consensus is reached if the owners of most coins have agreed on the state of the database. So when in proof of stake, we're talking about the computational power and the majority of this power. In proof of stake, this is the majority of money power. The majority of wealthiest users basically control the system. Examples are Peercoin, NXT, and Cardano, but for Cardano, it's not as simple because it has pretty complicated consensus mechanism, which works not the way I have described it. It's not just have more coins, have more rights. They have different mechanisms to ensure more fair and more an approach which protects from the abuse of powers. Basically, it's not easy to abuse your monetary power in Cardano. And overall, it is quite an interesting technology from the research point of view. Next is Byzantine fault tolerance consensus family. This is the whole group of consensus mechanisms which all rely on the problem of Byzantine generals that need to agree on whether they want to attack or whether they want to retreat. And these generals are making the decision presuming that some of them can be traitors. And the same mechanism was basically digitized and applied as a consensus mechanism for blockchain-based systems. Important difference of BFT consensus family is that the number of validators is known in advance. We have to know that in order to reach an agreement, because we will be exchanging messages between each other and evaluating the decisions of our generals. Validators are identified and know each other. So here we have a little bit of trust involved, but not necessarily, because if the group is big enough, we cannot trust all of them, and we do not need to trust all of them. We just need to trust that they are following the rules of the protocol. Adding or removing a validator requires the consent of others. Again, unlike Bitcoin or Ethereum or Monero or whatever, you cannot just jump in and start validating. You need to have an invite. Examples are Hyperledger and Quorum. And by the way, interestingly, Quorum is a protocol which is based on Ethereum, but was adapted specifically to be used in permissioned environments, in corporate environments, in consortiums, when several business entities want to use blockchain as the core of their accounting system. Here we have the visual representation. On the x-axis is trust in validators, less trust, more trust. On the y-axis, the anonymity of validators. So the permissionless public is proof of work. This is permissioned public proof of stake. FBA is permissioned but public. So you need invitation, but it's public. And permissioned private is PBFT, or even the use of multi-signature. So in this quadrant, we need to have the most trust into our counterparties. And in this quadrant, we have the least amount of trust. And basically, it's Wild West. What are some of the more concrete use cases for blockchain? First is settlements between banks, and this is what some entities are already very actively exploring, and some are even implementing some solutions. For example, the Central Bank of China, which has implemented its digital central bank digital currency, or CBDC, as it is often called. Many banks in Europe are exploring CBDCs. Banks and Federal Reserve in USA are exploring CBDCs. And as far as I know, some countries in Africa also have successfully implemented the pilot projects of implementing CBDC. And also, I'm proud to say that we, as the company, had a pilot project with the National Bank of Ukraine of implementing the test network for digital hryvnia as a CBDC. At the moment, this project is concluded, and the Central Bank of Ukraine is evaluating the results and planning the further development of digital hryvnia. Maybe, hopefully, in a few years, we will catch up with some of the most pioneering countries in this domain, and also maybe adapt a CBDC. Another use case is public registries. Again, whenever we need to have the data which is immutable, synchronized, reconciled, and available to be audited by third parties, this is where should we go? Blockchain. Auctions and exchanges. Again, here the rationale is due to the monetary financial nature of these transactions. It's the first reason, and the second reason is transparency. Many auctions operate without full disclosure, especially online auctions, and that's why you never know who is placing the bid. Is there any kind of convolution going on? Maybe the seller is bidding on his own auction to raise the price. This is absolutely not transparent, but in case when we want to build a transparent and fair auction, blockchain would be a good use case. The same goes for exchanges, when the again, the bids, the sells and buys are public and verifiable by the immutable ledger, and also not only the bids but also the transactions. So you will not have a situation when someone comes to you and says that they have bought they have exchanged some currency at a different rate than you remember. More interesting use case is DNS and PKI. These are more specific use cases, and they involve reliance more on the cryptography than on the blockchain, and the blockchain is used here mostly as again, this immutable reconciliation layer, but nevertheless, this is interesting use case to explore. And voting for the same reasons of transparency and immutability. And if we use digital signature as the instead of the paper of the pen signature on the paper ballot, it is easier to trace, and it is easier to confirm that it was really the person. And in fact, there are many more advantages, like more simplified and streamlined calculation of the ballots, instantaneous confirmation, less abilities for fraud, and so on and so on. Also, using cryptography, we can ensure the anonymity of voters, for example, using multi-signatures, or by using even zero knowledge proofs. We can ensure additional features in addition to simply it being instantaneous and verifiable. But again, this is a very big use case on its own. What are the complexities of projects that use blockchain technology? So the first is privacy, because whenever a project decides to use blockchain as its core technology, they need to answer the question how to store all transactions in a shared database, but not disclose sensitive commercial information. And again, there are many ways to solve this problem, and some are solved on the protocol level, some are solved on the business logic level, but it is nevertheless an important question to consider. Performance, we need to ask ourselves how to handle high transaction flow, and if there is a need to validate validators, which means if do we need to double check what they are doing, and how much trust do we have in the validators. Also, how to decide to update the protocol in decentralized environment. When we have client-to-server interaction, everything is simple. Server updates the software, client communicates with the updated server. Or when I have my phone, I get a notification to update the app, I update it, and well, it does not influence how the service works. For example, Facebook doesn't care what version of their app I use. This is my problem if I use an outdated version of the client. But for decentralized systems, especially when we are talking about breaking changes, orchestrating the protocol updates is critical process, because validators who do not accept breaking changes will not be able to participate in the new in the future of this system, because the rules will be new and they will be just left out, and we might lose a big chunk of validators and have this balance of power shifted to the wrong side. Storage, how to save only the minimum necessary data to save space in the blockchain, because whatever you put in the blockchain costs a lot, because storing data in the blockchain is really, 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 really expensive. And it gets more expensive the more nodes you have in your network. For example, if we have some blockchain-based system and the whole blockchain is 100 gigabytes, then for 10 nodes, it will be 1,000 gigabytes. For 100 nodes, it will be 10,000 gigabytes in total, and so on and so on. So no one wants to store this big amount of data. That's why you need to shrink whatever you put in the blockchain and store only the most necessary and the most concise pieces of data. Storing files, storing movies and music in the blockchain is not a good idea at all. Also, there's a question of responsibility, how to determine the culprit in case of conflict or error. Again, when the bank messes you up, you always know where to go. But when you, for example, I don't know, someone steals your private key and you lose all of your Bitcoins, there's no Bitcoin headquarters and there's no CEO, Mr. Satoshi Nakamoto, who you can sue, bring to court, or just go and try to talk to them. There's no such entity, and that's why there's always this question: who is the who to blame for protocol errors or for mistakes of the user? Next question is how to prevent situations where a small group of validators control the majority of the voting power. And this is the question of which is especially problematic for permissionless systems, because whoever accumulates power basically gains control over the network. For example, this is actually what we kind of see in Bitcoin, because the majority of power is concentrated among several mining pools. And you may say, yeah, but mining pools contain of different people who are in different places of the world and so on and so on. But the owners of the pools still have some authority over this computing power, and they have their own layer of software which can be used maliciously in order to manipulate the network. Next is how to reach a social consensus in an anonymous group that contains bad players. So how do we make everyone update, or how do we make everyone play nice, and how do we make everyone be good and validate only good transactions and so on? So this is like more of a social consensus question. What to do with the insider trading and fake news? So this is absolutely not the problem of the technology, because blockchain has nothing to do with trading, with news, with the price of the coin. It's all of the it's absolutely different. But whenever the project has some token inside of it, some coin or whatever they have that has some price, like a utility token, for example, there exists this problem of someone pumping the price and dumping the price, manipulating the price. And maybe the initial idea to have a utility token was noble, and it's to support the network and so on and so on. But unfortunately, what we see these days is that many projects practically died because their token became a target for manipulative trading and speculative trading. So this was it. Thank you all for listening. I see the counter on the chat button. We have quite a lot of questions. I believe my colleagues have answered most of them, but let's see if any of the questions remained unanswered, or maybe I could provide more context in the verbal form, in spoken form. How is the data updated in the blockchain? What happens to the...
No, Alex, you can see the last questions in the chat, because previous question for all questions exist answer in the chat.
Yeah, thank you, Olena. Looking at the bottom questions right now. Of course, I think on blockchain crash fault. What is the best way to solve blockchain trilemma at this moment? I would say there is no best way per se. There's better ways, worse ways, different approaches, and the thing I would say the best way is to to use common sense and to understand that some limitations are inherently hard or even impossible to overcome. Many protocol creators, they scream and shout and promise everyone that we have solved the blockchain trilemma. We are so smart and so genius that the blockchain trilemma is not a problem anymore. That's why go to our system, use our system, buy our coins, tokens, and use only our system. It's important to do your due diligence and to understand that some problems may be hard to solve, and that's why it's important to not take anyone's word for granted. That's what I want to say. Yeah, also I see additional context from our participants in the chat. And another question, what are the differences between CBDC and digital fiat money? Are the difference legal or technological? So from the technological standpoint, of course, we have some guidelines which were created by central banks. We have some models, some theoretical frameworks on how to build CBDC. It's important to understand that these are all recommendations, and CBDC is still a pretty vague concept, which everyone understands in their own way. So I would say technologically, the difference lies in the specific implementation and approach. So you can build digital fiat money with the same approach which would be used for CBDC and vice versa. As for legal differences, of course, each of them have their own legal trapdoors that you can fall into. The most obvious and the biggest one is that CBDC is controlled by the central bank of the country. The issuance and the management and the support is done by the central bank. Digital fiat money, well, I don't really, I cannot fully understand what are you referring to here, but I can speculate and say that you mean neobanks like Revolut and all these digital payment systems who create basically just normal money we have in the bank. In this case, the money you have in the bank right now, you don't have the money in the bank. You have an obligation from the bank to give you certain money. So this is not your money. Your money is only the one you have in your hand, in your pocket, the paper money you have. Bank has a very big problem with trust, just like any big institution, because it's centralized and you have no control and no transparency over what is going on inside of this institution. And that's why there is a big technological difference between CBDC and digital fiat money, because CBDC almost always presumes that there is a blockchain, that this system is blockchain based. That's why we get all of the benefits of auditability, transparency, more control. Cryptography is also a big point here, even though there is a challenge to make this cryptography user-friendly, because no one really wants to deal with private keys and all these complexities. And if we are talking about digital fiat, digitized fiat money, but with the system which is built on which is blockchain based, like I don't know, if we were to build one today, then the difference would be mostly in the legal field, because we can, again, as I have said, take the guidelines of CBDC and use them in our favor to build a digital payment system, kind of like Revolut, and to have this system, but in the private control. So I hope this answered your question. Okay, so we are right on time. So if there are any more questions, please let me know. Otherwise, I want to thank you all for participation once again, and see you in the next lectures. Maybe my colleagues also have something to say.
Sorry, can I ask another question? One final question.
Okay, please.
Thank you. I just wanted to ask, you've mentioned that proof of stake consensus is permissioned and public, right? Whereas proof of work is permissionless. So I was wondering, and obviously you also said that permissioned is where you have to get a permission to become a validator. So as far as I know, you don't, say, for example, in Ethereum, you don't need to have a permission. You just need to have a specific amount of coins that you stake in order to become a validator. So does it mean Ethereum is, permissioned, that you need to have these coins, or is it still permissionless?
Yeah, so the diagram that we had on the slide is mostly referring to kind of older proof of stake systems, more naive proof of stake systems that had dedicated lists of validators. And in such systems, just obtaining the necessary minimal amount of the coins is not really enough. You need to be included in the list, which is rotated based on the amount of money you have. So you need to either sign some smart contract or do something else to be included in the list. I will be honest, I haven't looked too deep into how staking in Ethereum works. But if it's automatic, so the moment you obtain necessary amount of coins, you are automatically picked up, and basically your software starts validating blocks, then it would be permissionless. If still after you have obtained the necessary amount of coins, you need to be included into some list which is rotated among the validators, then it would be permissioned. But well, unfortunately, I haven't looked that deep into staking rules of Ethereum, so I can only give you this like more high level explanation.
Thank you so much. I've played around with Ethereum staking, and I only needed a piece of software to run and a specific amount of coins, so I didn't need any permission from anyone to start this. So that's why I asked.
Yeah, then in this case for Ethereum staking, we can also put it into the category of permissionless systems.
Thank you.
You're welcome. Okay, so any more questions? Well, we still have some minutes left.
Okay. Thank you, Alex. Thank you all. Please wait for our test for you on this topic and check the classroom. And I think next time we'll see you on Tuesday next week, on the next week. And thank you and goodbye.
Yeah, thank you. Bye-bye all.
Bye-bye.
Thank you.
Thank you so
Thank you.
much. Have a nice
Bye.
evening.
Thank you, everyone.
Bye.
Bye-bye.